Okay. All right, guys. Welcome back to another week of the interactive sessions for the course Viscous with Flow. And we will begin by, continuing from where we left in the previous week, of course. And if you remember, so we were looking into scaling analysis of, the transport equations. In particular, we try to understand how different terms associated with the Navier-Stokes equation essentially scales. And the idea is to derive certain non-dimensional quantities because we, discuss the essence and the usefulness of, using non-dimensional quantities in our analysis. And we will continue it from where we left. And if you remember, we looked into the scales of certain variables. For instance, we looked into the scale for time. We looked into how the velocity and the stresses scales. And we also looked into how, the available length scales of the problems that we have at our disposal. So those were the premise. So first we went into seeing how the primitive quantities like the velocities and the lengths and the time scales is, and then once we know their scale, we looked into something. Uh, so we went ahead and saw how the more derived quantities like the stresses and for instance the stresses essentially how does it scale, and this is something that we saw, and then we ended our discussion by asking you to basically solve for basically look into the scales for pressure, and this is something that I asked you to try, and I hope you have joined. I mean, I hope you have tried this for at your end. So what we will do is we will start we'll start this session to the ones who just joined. We were basically recapitulating what we did in the previous week, and the objective now of this week is so we'll start it from by deriving the scales for pressure. uh, it would be a check if you did this at your end. It would be a check if at all, like if there are certain discrepancies which you might have find when you were probably looking for the scales for pressure. So we'll discuss this, and then once it is done, so it's just a small part. It won't take much of a time. It will just be over in 5 to 10 minutes. And once we do this, we will move now into a more, we'll move basically into a step ahead, and what we will do is we will use these characteristic scales that we derived, the non-dimensional variables that we saw, into solving certain class of problems, which a few of them you have already did in the theory classes, and you have already solved one assignment associated with it. But nevertheless, so we will what we'll do is the objective is to use these characteristic scales and the non-dimensional variables to actually solve those class of problems. We call it as time dependent solutions to 1D Navier-Stokes equations. For instance, you saw the Stokes first problem where there was a plate and there was a fluid, and the plate just moves with some velocity at time t equal to some 0 plus seconds. And on the other hand, the Stokes second problem is something that you saw that we had that same fluid, but now there is a plate which oscillates back and forth with some given frequency of oscillation and an amplitude of, let's say, some u naught. So these are at least the two problems you have saw. I mean, you saw, or at least you have analyzed in the theory classes, and I believe you have also solved assignment problems associated with these two problems. So we will be doing very similar things related to that, and we call it the transient solutions to the Navier-Stokes to 1D Navier-Stokes equations. But the the catch is we will solve a similar problem. I'll show you what the problem is. But the catch is we will now use the non-dimensional variables to actually solve this problem, and you will see and you will appreciate that using non-dimensional variables essentially give us much more insights into our problem, and at the same time it greatly simplifies our analysis because it reduces the number of parameters that we need to have a control on, and it just reduces to a single non-dimensional parameter, as we will see very shortly. And yeah, so this is the essence of doing non-dimensionalization in fluid dynamics. Okay, so this is something that I plan to discuss today. And before that, as I said, let's quickly look at what are the scales for pressure. And I believe if you have done it at your end, it's uh, you can just have a cross check with your answers. But before that, if you have any questions related to, the assignments that you solve, I believe the assignments for these class of problems has already been submitted by you. So the idea is that I will discuss some problems similar to that, such that if you have any doubts, the things get clarified. But apart from that, if there are any doubts related to those assignments and all, feel free to like ask me at any point of time, or you can ask me now, and I'll give you just 1 or 2 minutes to reflect on that. And then we will start off with the scales for pressure. So that's the idea. And as I said, please use, so you might also, so while you are solving the assignments, you might also encounter certain doubts. Please use the discussion forum then and as and when you happen to, uh, seek clarification for those doubts. And as you saw, like any one of the team members of the course will be there to assist you in this regard. And also the solution keys of the assignments are shared, and you can just go to your website and just find them in the tab. I think it's the last tab of the weeks contents, and you will see that there's something written solutions to assignment this and this. So you can just click that link and you can visit the solutions uh, to cross check your answers and to see if there are any discrepancies that you might find while you are solving the assignments. All right, if no questions, we will begin by trying to find out what is the scales, what are the essential scales for pressure. So what we will do is we will start off by writing our prototypical, Navier-Stokes equation, and we'll just write it in vector form, uh, just to keep things general. So as you know, the Navier-Stokes equation is basically the temporal term of the velocity, the temporal derivative of the velocity, and we have been doing it day in day out. So by now, I think this should be fixed at your memory how the Navier-Stokes equation basically looks like. So it's del u del t plus u dot grad u. Okay. Remember, this is the vector form that I'm writing. So that's why I'm putting an underbar u. So u bar is just ux ex plus uy ey plus uz ez. Okay. So I believe you are aware of this. This is the notation that we have been following from week one of these sessions. Okay. So yeah, so this is the right hand side which dictates the inertia term, and on the left hand side I have 1 upon rho gradient of the pressure plus nu del square of u, which is the viscous term, and I'm neglecting the presence of any body force. Okay, so that's the idea we have this. All right. Now, having said that, what we saw that we derived a characteristic scales for velocity, which was UC. This was basically how the velocity scale says. We derived the characteristic scales for time, which was TC. That is also something that we saw. And also we derived the characteristic length scale of our problem LC, which happens to be the channel length that we saw it in the previous week. So these three scales is something that we already derived. So I'll assume that we already know. We already know. Okay. So once these scales are known, our objective, okay, the objective is to find the scale for pressure. So what is the characteristic scale for pressure is something that we will try to figure out in this exercise. Okay. All right. So before that, just let's do a quick algebra. So what we'll do is, so this del u bar by del t, I can write that this term will scale as, I hope you know this symbol. This tells that this term is of the order of uh, the scales of the pressure, the scales of the velocity and the time. So del u by del t will essentially scale as uc by tc. I hope this is clear. What I hope you are clear on what I'm writing here. So this means that, just for a recapitulation, this means that this del u by del t is of the order of uc by tc. And we saw basically this in the last class, that if I have a quantity x which scales as let's say xc, and if I have a quantity y which scales as yc, so dx by dy will essentially scale as xc by yc. Okay. And remember, this is not exactly equal. It will be wrong essentially if you write del u bar by del t equal to uc by tc. This is absolutely wrong, because this is not exactly equal to UC by TC. This is, as I said, this just gives you a ballpark figure of how this del U by del T term would scale as, or it's how it's kind of like what would be the rough estimated order of magnitude of this term del u bar by del t bar, and it just scales as uc by pc. That's it. Okay, so then let's see how these terms scale. These terms scale u dot gradient of u. Okay, can you tell me how these terms scale now, given the exercise that we did in the last week? So you need to understand how these terms actually look like in order to find out what will be the rough order of magnitude of these term u dot grad of u. So, so here's something that you need to think. So if I expand this term, if I basically, expand this term, how would at least so this is the vector term, right? So it will have its own components. Okay. For instance, if I write this term in the x direction, if I write this term in the x direction, let's say, if I write, let's say, the x momentum equation, this term would essentially look like ux del ux by del x plus uy del ux by del y, and let's say we are in the 2D domain only. Okay. So this is how the expanded form of this term would look like. Now, from this, drawing analogy from this, I can say that since my ux or ui, this scales as some uc, so I can just write that u dot grad u will basically scale as, I hope you are with me on this will basically scale as uc square, okay, by lc. I hope this is clear, because this term would scale as uc by lc, and there is an ux already multiplied, which will of course scale as uc. So this term would scale as uc times uc by lc, and that's why it scales as uc square by lc. Okay, so this is the rough, again I repeat, this is the rough order of magnitude of how these terms u dot grad u would essentially scale as. Okay, then let's go into the other terms first. Let's see how these terms would scale like. So I have a kinematic viscosity, which is nu times the Laplacian of this velocity. And now drawing the same exercise, you can just say that this would scale as nu times uc by lc square. That is again because, if you write this term, if you expand this term, let's say once again in the x direction, it will just be, nu times del square u by del x square plus nu times del square u by del y square. And then just draw the same analogy that this term would just scale as nu times uc by lc square. And that's why, the order of magnitude of this term is what it looks like. All right. So what we did is we have looked into that how this and this term would roughly scale as in I mean we just saw that how the temporal term, the convective term, and the viscous term would roughly scale as, to be precise. Okay. Now given this, okay, we need to figure out what would be the scale for this term. Basically, something that we know, that we seek. So the pressure term, if you see, the pressure term is minus 1 upon rho gradient of pressure. So it is now obvious to say that this term would basically scale as Pc by rho Lc. I hope this is clear. Okay, we are not writing the minus term because we are just interested in the order of magnitude of what this particular term would scale as. It can be plus, it can be minus, but we just want to know that what's the magnitude. We just want to know that what is basically the ballpark figure of the magnitude of this term, and this is just Pc by rho times Lc, where rho is the density, Lc is the length scale, which we already know. That we already derived this, if you remember. So the length scale is, let's say, just for you to have a recap, the length scale is, let's say, the height of the channel, which we already saw it in the last class. So having said that, I hope you realize that the objective is to just determine this Pc. That's it. Because every other scale, that is Lc, Tc, Uc, these are all known from the problem that we are solving. Okay, so I'll write it down. So we need to find Pc. That's it. All right. But in an attempt to find this Pc, we face a dilemma here. Okay, and I'll tell you what is the dilemma in this context. So I can say, so I have two options here. I can say that my Pc, that my pressure term, that this term can scale as this term basically. Okay, I hope you understand, because let's say I have a fluid, okay, where the inertia is very much negligible, meaning that this term basically goes to zero. Then I can say that my pressure term would basically scale as this term, and then I can have an expression for PC by equating the order of magnitude of this term to the order of magnitude of the viscous term. Okay. In the other hand, on the other hand, I can also say that my pressure, can also scale as the inertia term. For instance, I can say that my pressure can scale as this U dot grad U, which is the advection term, to be to be precise. Okay. So now this is what the dilemma we face, because pressure can either scale as this, or pressure can either scale as this advection term. So which one is to choose is something that we'll try to figure out. Okay. So then we'll take it, a step by step. So we have one option. So the first option is, my pressure, the pressure term can scale as the viscous term. Okay. And in that context, I can say that this PC, that this PC by rho LC, because this was the scale for the pressure term. So this PC by, rho LC, this would scale as the viscous term, where the viscous term, the scale for the viscous term is just UC square by LC. Okay. So my PC by rho LC would scale as UC square, by LC. And then if I cancel this, then did I make a mistake here? Sorry, this is the inertia term. So I wrote the inertia term instead of the viscous term. So the first option is that the pressure can basically scale as the advection term or the inertia term. So because this UC squared by LC is essentially the advection scale. So it's not a viscous scale. So it's just the advection term is what the pressure term would basically scale as. Okay. So yeah. So then I can have that my PC will scale as rho times UC squared. Okay. So this is one option. Okay. So this is one option. So as to what dictates what the pressure term in my analysis can scale as. Okay. So the idea is I just equated the pressure term to the advection term to eventually find out that this is what my pressure term would scale as. And this is called the advection scale for pressure. Okay. This is called the advection scale for pressure. Okay. Now I also have the second option, as I said, that so in the second option, what I have is my pressure term, that is this term, can also scale as the viscous term, which is basically nu times del square of u. And if I do that, let's say what we get. So if I just say that my pressure term scales as the viscous term, and my pressure term is what? It is just PC times rho LC, and the viscous term is nu UC by LC square, if I'm not wrong, because yeah, so this is basically the viscous term, which is nu UC by LC square. And then if I try to calculate what PC would be, I would simply get PC to scale as, PC will basically scale as rho nu UC by LC, or I can write it as, so nu is basically mu by rho, so this will become the dynamic viscosity mu UC by LC. So so this scale, so we end up getting two distinct scales for pressure, if you realize. So just by equating the sorry. So just by equating the scale for pressure in first with the advection term, and then second with the viscous term, I get two distinct scales for pressure. One, the advection scale, which is just rho times UC square, and the other, the viscous scale, which is mu UC by LC. And this is known as, the viscous scale for pressure. Okay. Now we derive two scale by taking two options, because these are the options that we had. So we just naively just said that once, pressure will just scale as this term, and then the pressure will scale as the other one, that is, let's say, the viscous term. But which term to choose, because we can't have two scales for a single problem, right? So which term to choose is actually what, is what makes the scales for pressure interesting. So the truth is, and the reality is, pressure can scale as either of these two scales depending on the Reynolds number of the problem. Okay, if my if my Reynolds number is very small, then pressure PC would scale as the viscous term, and it would be just mu UC by LC, that is the viscous scale. And if my Reynolds number is very large, if my Reynolds number is very large, then pressure can scale as the advection scale, which is rho UC square. Okay, so now it's, I hope you realize that pressure has two options. We have two options to basically choose the scale for pressure, and it's the Reynolds number which dictates what the scale of pressure in my problem is going to be. If I have a viscosity dominated flow, pressure would scale as the viscous term. Pressure would scale the scale for pressure would be the viscous scale for pressure, which is mu UC by LC. If I have a advection dominated or an inertia dominated flow, pressure would just scale as rho times UC squared. Okay, so this is the diffusion scale. This is the diffusion scale, and this is the advection scale. Okay, all right. So this was something that I asked you to do. I hope you also end up getting these sort of at least you tried to do it, and I believe you have just got something similar of this sort. And if not, like, I hope you will watch this video and get clarifications on where the things might have gone wrong at your end. Okay, so I believe this ends the theory behind the scaling analysis. And as I said, we will now move into solving a more, realistically, some more realistic problems. and and yeah, so that's the idea, as I said. So I'll explain what we are going to solve, but before that, like, if you have any questions on any of the topics regarding the things that we did so far, you can go ahead and just ask me. We'll stop here for 2 minutes, and then we'll begin the discussions on the things that that I plan to say in the later part. Okay. Okay. All right. So if no questions, so now what we did is, if you remember, the until now that we looked into the scales, and prior to that we looked into some special class of problems where we seek, exact solutions to the Navier-Stokes equations by making certain assumptions. For instance, we looked into, the unidirectional rectilinear flows, then, the axisymmetric flows, where you essentially saw that you basically ended up, getting an ODE, and we just need to solve that ODE by, enforcing the correct boundary condition. And that was the idea that we saw. Okay. Now what we will do is, and then of course we looked into the scaling analysis, because I argued that, see, the scaling analysis is an option. Okay, you can also solve the governing equation dimensionally, but getting insights into the velocity profiles when the problem becomes complicated is something that is difficult if you approach a problem dimensionally. And that's why, it becomes easier if we non-dimensionalize the problem, and that is typically the reason why we learn the scaling analysis. And I hope that by this exercise you will convince yourself that indeed the scaling analysis is helpful. And you will see that by the end of this class, and uh, at least by the end of this class, and then in the subsequent classes as well. That the power of, the non-dimensional variables is profound, is what I, tried to say. All right, but nevertheless, the thing is, now we will we will move into a more generic class of problems where instead of solving ODEs that we just did, we will basically be solving partial differential equations, which means that we have indeed increased and one order of complexity to our analysis that will now move from ODEs to PDEs. And one such class of problems are time, transient problems basically. Because if I have a transient problem, I know that my velocity, let's say, would always vary with space. That comes from the physical nature of the problem. And if I am now, looking into unsteady, cases, okay, then time also comes either as a variable or as a parameter, as we will see. Okay. So we will be solving such kind of problems in this context. But the idea is we will non-dimensionalize the problem first and then look into its solution. And in that context, it will also give us an idea of how non-dimensionalization essentially helps in simplifying our analysis. Okay. You have already seen two of such problems in your theory classes. One such problem was, if you remember, it was the Stokes, it was the Stokes first problem. Okay, where if you just remember, there was a plate, okay, and you had just this is just a recap that I'm giving. You had a fluid that was sitting on the top of this plate, okay, and you have an axis system, whatever be it. Let's say this is my x and this is my y, and the idea is that you give this plate a push in either of the direction, that is the plate velocity, with some, let's say, up. So what you are doing it, at time t equal to 0 plus seconds, you are basically moving this plate with some velocity up. Now the idea is when you move this plate, on account of the fluid being viscous, the fluid will also move in either of these direction or this direction, depending on which direction you are actuating the plate, with some velocity. Okay, and this was typically the Stokes first problem. Now if you remember, in this problem, you use something which is known as a similarity solution approach, that you choose the similarity variable eta, which was of the form, let's say, y by some square root of x of this form. And then, sorry, it was some y by, square root of t. I mean, this was some form that you choose. And you choose this form, you know, basically because you didn't have a defined length scale or a defined time scale in your problem. Okay. So what you did is in the Stokes first problem, you basically use the similarity approach. Okay. And define a similarity variable eta. Let's say, so this was the similarity variable. This eta was a function of y and t. And then what you did is you use this similarity approach into, converting the PDE into an ODE. However, a very similar problem, which we call it as the Stokes second problem. Okay. So this is basically the Stokes second problem, where you saw that we had a similar setup, that there was a plate, okay, and there was a fluid that is sitting on top of this plate. Just a similar setup like this. The only difference is that I hope you realize is that now at time t equal to 0 plus, instead of giving a constant velocity to the plate, you oscillate the plate with some known frequency omega. That is, this plate basically now oscillates. So the plate now oscillates with some frequency omega. So now, instead of giving a push to the plate in either of the directions, in just one direction, what you do is you just make the plate oscillate with some, let's say, up as some u naught cos omega t, where u naught is the amplitude and omega is basically the frequency with which the plate oscillates. Okay. Now, just by giving this tweak to the earlier Stokes first problem, your entire methodology for the solution changed. And if you remember, what you did is you seek something which is known as time periodic solution. That is, you now know that you will ignore the initial transients of the of the solution, and you will say that since my problem is an oscillatory problem in time, I will look into the velocity profile, and what you say is that you basically look into the velocity profile, which in turn will be oscillatory. That means that the fluid will oscillate as and when the plate oscillates, with a phase difference, of course, because if the because that phase difference yeah, basically arises because of viscosity. Okay, so that is the essential difference between the Stokes first problem and the Stokes second problem, at least fundamentally. But the solution procedure changed, because now what you are doing is, since you know at what frequency the plate oscillates, you have a defined time scale in the problem. Okay, so here you have a defined time scale, and this time scale is nothing but the frequency, the inverse of the angular velocity with which the plate oscillates, or the frequency would be twice pi of the angular velocity. Okay, so the time scale would be the inverse of that. So it is just inverse of the angular velocity with which the plate oscillates. That's the idea. No, so now since you have, so in the Stokes second problem, since you have a defined time scale, you basically no longer need to use the no longer need to use the similarity variable, and what you seek is something which is known as time periodic solution. That is, you will ignore the initial transients, and since the fluid is assumed to be the fluid will, so it's like that you are also assuming that the motion of the fluid will also be oscillatory, just like the motion of the plate, but they will have a phase difference. Okay, and that's so, and because of that, what you did is you assume that the solution of this of the form of the fluid, let's say the x direction velocity of the fluid, which will be a function of y and t. What you did is, this is you consider it as some real part of u hat of y e power I omega t. So this is something that you choose as a form of the solution for this problem. Now you need to realize that this is possible because the governing equations are linear, and of course the first thing is that the governing equations are linear, so you can use this form. And the second is that you are now looking for time periodic solutions. That is that you will bypass the initial transients of the plate, because you know that the fluid will also oscillate as and when the plates does, with of course a phase difference. And that's why this is basically the fundamental difference between the Stokes first problem and the second problem. Mathematically, in the Stokes first problem, in terms of the scales, we do not have a defined length scale, neither we have a defined time scale. And that's why we use something which is known as the similarity variable. In the Stokes second problem, we have an imposed time scale in our problem, which is nothing but the inverse of the frequency with which the plate oscillates. So we have an imposed time scale, we have an imposed length, we have a length scale, we have a velocity scale, which may be just u naught. So we just have two scales. We just need to figure out what will be the length scale of the problem. And that's why we didn't use similarity approach in the Stokes second problem. Rather, we look for time periodic solutions, because now we have a defined time scale of omega inverse, and of course because also the governing equations are linear. So this is the idea behind time periodic solutions. Now we will not solve these two problems, because this is something that we already did. What we will do is, drawing motivation from specifically the Stokes second problem, we will now look at a problem which I call it as time periodic pressure driven flow in a cylindrical pipe, which is similar. The analysis will be similar to Stokes second problem, but the paradigm is different. Okay. And this is the problem that we will be solving. Okay, so I'll stop here for some time, and then I'll physically put forward. So we'll proceed very slowly, but we will understand this, and of course we'll be doing this non-dimensionally, and this will help you to give you a flavor of how powerful non-dimensional equations are essentially, and their solutions. Okay. So this is the idea. So I'll stop here for some time, and I'll let you to basically think about what we just now discussed regarding the Stokes first and the second problem, and then subsequently going into the solution of this transient yet periodic pressure driven flow in a cylindrical pipe. Sorry for this typo. It's just this. All right. Okay, so I hope you understood what we basically discussed until now. So this is something that we will look at. So the next problem. So the problem is something like this. So we looked into, axisymmetric problems where, there is a fluid flowing through a pipe and you apply a pressure gradient which is constant, let's say some G naught. And then we saw that the velocity profile is essentially parabolic, at least in the developed, hydrodynamically fully developed region. And we solved the usual basically the second order, ordinary differential equation governing the z direction velocity of the flow. And then we saw that uz is essentially a function of r square, which argued that the velocity profile is periodic. Now, this was the special case when the pressure gradient is just a constant, let's say g naught. The only complexity that brings that distinct, that differs in this problem and the previous problem, which is nothing but the Hagen-Poiseuille flow, is that instead of now applying a constant pressure gradient, we will say that the pressure gradient is now not constant, but it is a periodic, so it is periodic in nature, and that's why I call it as time periodic pressure driven flow. Okay, that is the driving force, which is the pressure gradient of the flow, instead of it being a constant, which is the case in case of Hagen-Poiseuille flow. But now it is not a constant, but it kind of, it's kind of an oscillating pressure gradient. So if you think about it closely, a realistic scenario which uses this kind of model is like is our human heart, which basically pumps the blood periodically. Okay, so if you want to model, the flow of human blood, in veins and arteries, but remember, veins and arteries doesn't have fixed length, because they can expand, they can compress, but this is just a very crude model that I'm saying, that if you want to model the flow of blood, let's say moving through a fixed pipe, which is of the order of, let's say, which is very small, it's just a crude thing that I'm saying, then at least the pressure gradient that you will choose to basically actuate the blood flow has to be, an oscillatory pressure gradient. I think that is something that you should realize. It cannot be a constant pressure gradient, because in one cycle, the heart basically, you know moves the oxygenated blood, and in the other cycle, it brings in the deoxygenated blood. And I mean, I hope you understand what I'm trying to say here. Okay, so it's kind of a periodic motion of fluid that happens in such scenarios. Okay, so at least the pressure gradient, if you want to model it has to be an oscillatory pressure gradient, instead of it being a constant pressure gradient, at least in these kind of scenarios. So now, drawing motivation from such physical examples, what we will see is, we will now consider a pressure gradient of a fluid which actuates the flow, of course, to be an oscillatory pressure gradient. And for now, we'll consider that we are still in the hydrodynamically fully developed region, so we'll neglect the beginning and the end effects. That means that the pipe extends to a very long distance, and this zone in which the analysis is valid, we'll consider it as the fully developed zone. Okay, that's the idea that we will consider here. So having said that, the objective is, so this is the physical picture, and that we have with us here. So the objective is, if you can see in my screen, what we need to do is, see, the ultimate objective is to get the velocity profile, just what we did in Hagen-Poiseuille flows, Couette flows, planar flows, and all those kind of things. And of course, just what you did in the Stokes first problem and the Stokes second problem. And this is something that we will do here also, that we will get the velocity profile. But in an attempt to finally get the velocity profile, what we will do is, we will first identify the appropriate characteristic variables in this analysis. That the theory that we learned in case of the scaling analysis, we will apply it here to identify what will be the appropriate characteristic variables, and then use these characteristic variables to derive non-dimensional governing equations and boundary conditions. So we'll be using these characteristic variables to figure out what will be the different non-dimensional parameters. Okay, and also use that non-dimensional variables basically, and the parameters, of course, in the governing equations and the boundary conditions. And once it is done, what we will do is, we'll solve the governing equation, of course, to obtain the velocity profile. That's the three objectives that we will try to focus on as a part of the analysis of this problem. Okay, I hope the objective and the physical picture of this problem is clear to you. All right, so then let's get started. I hope the picture is clear. So let's get started. So as I said, we will always start problems of this sort with the assumptions. Okay. So the first assumption is that we will also, just like the previous flows, we will still consider this flow to be unidirectional. So it's a unidirectional flow, which means that my ur and my u theta components of the velocities are zero identically, and I will just have a non-zero uz of velocity. But now this uz of velocity will be a function of r, and it will be a function of time, because the pressure gradient is oscillatory in nature. Okay, and of course we'll consider the flow to be fully developed. Okay, this, so by now you understand the consequence of this fully developed flow. So if you just apply this idea by using the continuity equation, you can eventually show that your uz, which is a z direction velocity, this is not a function. So meaning that uz, which is a z direction velocity, this is not a function of z. Oops, sorry. So we have done this many a times. Just apply, just write the continuity equation. You will eventually see that del uz by del z is equal to 0, which means that your uz is not, so it is basically not a function of z. That comes from the fully developed flow, meaning that your uz can at most be a function of r, or your uz can be a function of time. Okay. All right. And then one more assumption is that, the flow is essentially axisymmetric, because theta dependence we are not considering, so we'll not write that. And of course, like it is constant properties, we can write this. That means that all the properties, for instance the viscosity, you know so what properties do we have? We have the viscosity, the dynamic viscosity, and the density. These are constants, and they are not a function of space or time. Okay, but again, that's an assumption that we are considering. So based on this assumption, let's now see the different characteristic scales that we can define in this analysis. Okay, so the step one, so we'll do this very systematically. So okay, so the step one, but yeah, before going into the characteristic scales, let's write first the governing equations. So now I hope you realize that since we just have a one directional velocity, we'll just have to write the z directional velocity equation. Okay, so, and of course I'll not write it from the initial, I'll not write all the terms here, because just invoke these assumptions, and you will see that the z direction, and of course you will see that the z direction equation essentially simplifies as follows. Okay, so the z component of the Navier-Stokes equations simplifies, the simplified form of which is as follows. It is just rho del u z by del t, and then I have minus of del p by del z plus mu by r del r of r times del uz by del r. That's the simplified form of the z direction equation. I'm not starting from the big form, because that is something that you are expert, that you have to, I believe you are just experts of these, you know these things, at least by now, because we did this, repeatedly in the previous sessions, and also in the the week's lecture series. Okay, so just for a check, what you do is just write the entire z direction equation, invoke all the assumptions that we just said, and you will see that you will just end up getting this equation basically. All right. Now, since we know that this dp by dz is just some g naught of cos omega t, so we'll just write it that this is just rho times del uz by del t, and this is some g naught of cos omega t plus mu r del r of r times del uz by del r. All right. So typically, I'll name the equation. So this is the equation one. So typically this is the equation that we'll try to solve. But as I said, we will we will try to convert this equation into a non-dimensional equation and try to solve the non-dimensional equations uh, in the analysis. But that we will do. But before that, let's also, but yeah, the more important thing is I hope now you realize that this is essentially a PDE, that this is a partial differential equation in case of an ODE, which we earlier saw, that all the analysis that we did before this or prior to this, those were, ODEs in nature. So the solutions were either known or it was very easy to basically evaluate, okay? But this is not the case in case of PDEs. PDEs are very nasty equations because at least you have just realized by see the Stokes first problem and the Stokes second problem is more or less similar. It's just how one plate just moves with the velocity and in the second place one plate just oscillates with some frequency. The you can argue that the amplitude of the velocities are just not which are just same, but the very procedure of solving the PD is changed when there is just a tweak of that oscillatory thing that comes into the picture. So I hope you appreciate that how rich the solutions of PDEs are. That a little change in the physical system brings about a change in the solution procedure of partial differential equations, which is not the case in case of ODEs. So that's why PDEs are I would say they are I would say they are nasty in the sense because we don't have a defined procedure a priori. We have to look into the physical system in order to devise a strategy for solving a partial differential equation. And this is something that at least you have realized when you solve the Stokes first problem and the Stokes second problem. And at the same time, they are also very rich because the solutions that you get, this this has they have the power to give you tremendous insights into the physics of the problem. Okay. All right, so quickly let's see the boundary conditions also. So the boundary conditions are, so the usual no slip because of the fact that the fluid is viscous and the walls are stationary. The fluid velocity here and here is that uj at r equal to capital R is just g is at r equal to capital R is just 0, and that is that is the first boundary condition, is that uj at r equal to capital R for all time is 0, and this is the usual no slip. And the second boundary condition is that, see, the velocities at this and this point is 0, meaning that in the entire profile, whatever be the profile for uj has to be bounded. So this is the second boundary condition. Okay, so uj is bounded at all r for all time. Okay, so these are the two boundary conditions that we'll use. There's also an initial condition. You can say that the initial condition is, you can say, you can argue that your uj at all r, but for the time when t is exactly equal to 0 is 0. This this can be the initial condition, but we will see that we no longer need to use these initial conditions, because as I said, we are seeking time periodic solutions where we say that okay, we are neglecting the initial transients, and since the fluid will also oscillate with time because of the fact that the governing equations are linear, I will look into the scenarios where I will bypass the initial transients and then look into the oscillatory behavior of the fluid when the pressure gradient essentially oscillates. So that's the reason why, even though there is an initial conditions, we will not require the initial conditions, okay, for this analysis. And this is also something that you saw in the Stokes second problem, I believe. Okay, so we'll stop here once again for some time. I will let you guys to essentially think about, so as to what we did, that how the governing equations is formed, what are the boundary conditions, and then from now, in the next step, we will choose the various characteristic scales and we'll look into the solution procedure of this problem. But before that, I'll fill my mug with some water and I'll come in just 1 or 2 minutes. Okay. All right, guys. Sorry for the interruption. Okay. So now what we'll do is, as I said that, yeah. So the thing is, you can also solve these equations in a dimensional form. That's completely fine. But since we said that we'll also bring in the picture of the scaling analysis into this problem. We will solve this problem non-dimensionally, and we will see that yes, indeed, non-dimensional solutions helps. And this is also a part of the analysis that we are supposed to do while as a part of the solution of this problem. Okay. So the step one, as I said, that is the first objective, as you can see, is to identify the appropriate characteristic variables. Okay. So so I'll write it that step one is that choosing the characteristic scales. Okay, so let's do it, guys. So I hope you now understand that in this problem, you can say that you have you have a distinct time scale of your problem, because you know with what frequency the applied pressure gradient so at what frequency the applied pressure gradient works, basically, which is just omega in this case, or 2 pi omega is the frequency. Okay. So in a way, you know that your characters, so basically, since the frequency is known, you have an imposed time scale of your problem. So the characteristic time scale, which we call it as TC, is nothing but omega inverse. That is the imposed time scale that we have. Remember that we saw a problem where there is a bird who flaps with wings, flaps basically its wings with some given frequency omega. So I said that this is a problem, that if you are looking into the disturbance of the fluid, which is very next to the wings of the bird, the time scale of the disturbances will be the imposed time scale of the problem, which is omega inverse. Okay, so that's an imposed time scale that we basically have. Okay, so I'll write it down that TC is omega inverse, which is the imposed time scale. If we don't have an imposed time scale, we will look into the other time scales, which is the advection time scale and the viscous time scale, which we also saw. Okay, but here, since we have an imposed time scale, we will consider our TC to be omega inverse. We, we also have a characteristic length scale. And this characteristic length scale, which we call it as LC, is nothing but the radius of the pipe. Because remember, the length scale, we will choose that length scale moving along which we see there is an appreciable change in the velocity. Now, the length of the pipe here cannot be a length scale, because you know that the flow is essentially fully developed. So if you move along the length of the pipe, you will not see a change in its velocity profile. Rather, if you move along, the radius of the pipe, you will indeed see that your velocity profile indeed varies. So the physics of the problem is captured if we choose the length scale to be the radius of the pipe, is the essence why we choose the length scale to be equal to r. Okay. So LC is r, which is nothing but the pipe radius. So given these two scales, we will now see that do we have a characteristic velocity scale? Because now, but just by looking at the problem, we are unable to figure out what will, unable to, just by looking, it's not possible to figure out what will be the characteristic velocity scale. But we will see that from the knowledge of the amplitude of the pressure gradient, we will have a characteristic velocity scale. And this is how we will do this. So what we will do is, in order to evaluate the characteristic velocity scale, we will say that the pressure gradient term will scale as the the viscous term. Okay. And in that context, what I will say, so the meaning is that for the characteristic velocity scale, what I'm trying to say is that the order of magnitude of minus dp by dz is of the same order of magnitude of mu by r del r times del uz by del r. Okay. And I know that the order of magnitude of minus del p by del z is just g naught. This is typically because I know that my pressure gradient, that is the applied pressure gradient, is equal to g naught cos omega t, but cos omega t is just a periodic term, okay, which will oscillate between +1 and -1, which means that the rough ballpark figure of dp by dz will just be dictated by its amplitude g naught. It is the amplitude which will dictate the ballpark figure of the magnitude of the applied pressure gradient, and that's why we say that dp by dz will scale as g naught, will just scale as g naught. And then similarly, the term on the right hand side, that is the viscous term, this will just scale as mu uc by what? By r square. Because this term would basically scale as mu uc by lc square. Okay, because this r and this r would get cancelled. They will have an lc square coming from this point, and we'll have a uc that will come from this point. And that's why I say that this term would basically scale as mu uc by lc square. So this means I have a velocity scale for also our problem. So this is kind of a derived scale for velocity, which means that my uc would scale as g naught times rc square by mu. Okay, so this is the velocity scale that that we get from the problem. Yes, I understand that we don't, just by looking at the problem, we don't find the velocity scale, but the velocity scale can be evaluated from the knowledge of the applied pressure gradient. Okay, and that's what we did to evaluate what will be the velocity scale of the problem. All right. So now the first task is done, that identifying the different scales of the problem are finished. So what's next then? So the next immediate task is to, define the non-dimensional variables using this characteristic variable. Okay. So the step 2 is, defining, I call it as defining the non-dimensional variables. Okay, but these non-dimensional variables are based on the chosen characteristic scales. Okay, so in all the analysis that follows from this point now on, we will denote any non-dimensional variable with a bar over its letter. For instance, I will define my non-dimensional uz component of velocity as uz bar, and this is nothing but your dimensional uz divided by your characteristic uz, which is uc. Okay, and uc is just this g naught r square by mu. Okay, similarly, my non-dimensional radius r bar is going to be r, the dimensional radius, by lc, and your lc is nothing but the radius of the pipe, which is just r. And in the same way, your non-dimensional temporal variable t is just the dimensional counterpart divided by lc. lc is nothing but omega inverse, because it is, sorry, not lc, sorry, it is t by tc, and your tc is omega inverse. So this just simplifies to omega times t. So your non-dimensional time t bar is just omega times the dimensional time. Okay. So these are the non-dimensional variables of our interest. So once the non-dimensional variables are defined, it now becomes obvious that in order to non-dimensionalize our equations, what we will do is we'll substitute these non-dimensional variables into the dimensional governing equation. And that's what we will do it in the next step. So the step 3 is, in order to evaluate the non-dimensional governing equations, we'll substitute the non-dimensional variables into the governing equation. To get the non-dimensional governing equations. Okay, so we have the governing equation here, that is equation 1, and we have these boundary conditions, which is equation, let's say 1a, and this is 1b. Okay, and let's call the initial conditions, although we don't require it, as 1c. Okay, so if I now substitute all the non-dimensional variables into these equations, so let's see what the first term would look like. So the first term is what? It is rho times del uz by del t. But we know that uz, which is a dimensional z direction velocity, is the non-dimensional velocity multiplied by uc, because this uc will basically go there, which means that I can write this term as rho times del of uc times uz bar. Okay, by the same thing for time, I can write it as tc times t bar. Okay, but see, these characteristic variables are just some constant. These are mere constants. Okay, which means they will just come out of the integrals, sorry, the differentials, and this would be rho times uc by tc times del uz bar by del t bar. And we know what is uc and tc. So this term can, so this term just simplifies to rho uc, where uc is this, so uc is just g naught r square by mu, so I'll just keep it as uc, where you can always substitute uc as g naught r square by mu. Tc is omega inverse, so I'll just write it as omega basically. Okay, and then this term is nothing but just del uz bar by del t bar. So this is essentially, the what you can say, the derived non-dimensional form. This is the derived non-dimensional form of the dimensional form of rho times del uz by del t. Okay, the similar exercise you can do it for the other terms. For instance, this term, the non-dimensional form of this term would be g naught times cos omega t is just t bar, so this would be just g naught times cos t bar. Okay, so the other term, the g naught times cos omega t, its non-dimensional form would be just g naught cos t bar, because we just now saw that t bar is nothing but omega times t. The third term is this term, and let's see what these terms, let's see the non-dimensional form of these terms. So we have mu by r del r of what? Okay, so it's mu by r del r of r times del uz by del r. And then if I do the same analysis for this term would eventually be, you can check it at your end, it would be mu uc by r squared times 1 by r bar del r bar of r bar times del uz bar by del r bar. I hope you are clear on this one. Okay. All right. So this is precisely the non-dimensional form of the dimensional form of mu by r del r of r times del uz by del r. Okay. So now once we derived all the non-dimensional forms, that these, we'll just substitute these forms in the governing equations. Okay. So the governing equation does turn out to be something like this. It just turn out to be mu times uc by tc. Tc is just omega, which is this, times del uz bar by del t bar, and then we have the terms on the right hand side, which is g naught times cos of t bar plus mu uc by r squared times 1 by r bar del r bar of r bar times del uz bar by del r bar. Okay. All right. So now what we'll do is we will substitute uc as this term, because we already evaluated uc. So uc is g naught r squared by mu. So we'll just substitute it. So this uc now becomes, the uc is just g naught r squared by mu, which means what? Which means that this g naught and what? And of course this uc also becomes to be g naught r squared by mu, which means that this g naught will get cancelled, this r square and this r square will get cancelled, and this mu will get cancelled. So we just end up getting rho times mu r square, sorry, rho times omega r squared by mu del uz bar by del t bar, and then we have cos of t bar plus 1 upon r bar del r bar of r bar times del u z bar by del r bar. Okay. All right. So let's do one thing. Let's simplify this term and we will see a interesting thing here. Okay. So I can always write this term as something like this. It is rho omega r times r by mu and del u bar by del t bar, and this is cos of t bar plus 1 upon r bar del r bar of r bar times del u z bar by del r bar. Okay, so if you take a closer look at these terms, so what does this term look like? It is rho times omega r is a velocity times a length divided by mu. So it sounds something like Reynolds number, and we call this term as a frequency dependence Reynolds number. Okay, we call this as frequency dependent Reynolds number. And we will denote this frequency dependent Reynolds number as alpha squared. Okay, so the ultimate non-dimensional, so ultimately the non-dimensional equation basically looks like this: alpha squared times del uz bar by del t bar is equal to cos t bar plus 1 upon r bar del r bar of r bar times del uz bar by del r bar. Okay, that's it. That's the non-dimensional equation that we will seek to solve from the given dimensional equation. So now, and I'll name this, so let's name this equation as some 2 maybe. So I'll call it as equation 2. Okay, so this is it. So this is the non-dimensional equation that we get. But I hope you can realize that in this non-dimensional equations, I just have a parameter alpha that just appears, which is some kind of Reynolds number. Okay, so you can now appreciate that the solution, which is just uz bar, this can be uniquely determined if I specify alpha, basically. Okay, meaning that of course uz bar will be a function of r bar and t bar, but it will be a function of this parameter also, meaning that it is just that. So I mean to say that instead of defining different properties of the fluid, if I just specify this alpha, we will get a unique solution for a unique value of course r and t for uz bar. Okay, and this is where the power of non-dimensionalization lies. Okay, because I no longer have to independently say what is the viscosity of the fluid, what is the density of the fluid, and so long and so forth. I will just say that okay, this is my frequency dependent Reynolds number, and give me the velocity field for this frequency dependent Reynolds number, meaning that the velocity contours or the velocity field, I would say in this case, is just a function of this frequency dependent Reynolds number in non-dimensional analysis. And that's where its power lies, because it kind of becomes now universal. I don't have to specify the different densities, the different viscosities. Rather, I will say that okay, what is the frequency dependent Reynolds number, and this will uniquely give me the velocity field of my analysis. Okay, and I hope you realize that this is why we do non-dimensionalization essentially. Okay, so once this is done, let's also write down the non-dimensional boundary conditions also. So the non-dimensional boundary conditions. Okay, so so the first boundary condition, if you remember, so the dimensional form was that uz at r equals to capital R for all time is equals to 0. So the corresponding non-dimensional form of this would be uz bar at r bar equals to 1 at all t bar is basically equals to 0, which is just the no slip. And I hope this is easy for you to interpret, because now this r bar, which is just r by capital R, will just be 1 when r is equals to r, because of the fact that my r bar is, if I write it, because of the fact that my r bar is just the dimensional radius divided by the radius of the pipe. So at r equal to capital R bar is just 1, is something that I tried to say it here. Try to say here. Okay. And the second is of course the boundedness, which means that my uz bar with its magnitude is bounded. Okay. So these are, the two non-dimensional, so these are the two, I would say non-dimensional, okay, not this. This is the dimensional one. This is the non-dimensional one. And this is the non-dimensional boundary condition corresponding to the non-dimensional equation 2, basically. Okay. All right. Okay. So we also finish one more objective, that is we derive. So we choose. So we have, chosen all the characteristic scales based on a physical picture of the problem. We define the different non-dimensional variables. We substituted the non-dimensional variables into the governing equations, into the dimensional governing equations to get the non-dimensional governing equation, which was equation 2a. And we looked into a parameter that came out, that popped out of this analysis, which is nothing but the frequency dependence Reynolds number. Okay. Now we are still not done yet, because this is something. So this is just some, you can say these are the initial things that we did, but still we need to evaluate the velocity profile, which is this uz bar of, which is this uz bar. And for this we'll now look into the solution procedure of this problem, which is step 4, that is the solution procedure. But before that, I'll stop here for a couple of minutes. If you have any doubts, you can feel free to ask. Okay, all right. All right, guys. So now let's look into how the solution of this governing equation 2 will, subject to the two boundary conditions 2a and 2b, will appear to be. So this is where we'll use the idea of the Stokes second problem. Okay. So we will assume that uz bar, which is a function of r bar and p bar, to be of this form. So we'll assume that it is something of the form real part of u hat of r bar times e power I t bar. Okay. Similar to the one that you assume for the Stokes second problem. Now the idea is twofold here. Okay. We did this assumption. I mean, we are in a position of making this assumption mainly because of two things. First, the governing equation is linear, as you can appreciate that you can just have a look at the governing equation 2, and this is indeed linear. So since the governing equation is linear, so I can say that the solution can be interpreted to be linearly proportional to e power I t bar. Okay, and that's one of the prime reasons why you can assume this form of solution. So if there are the non-linear equations, we cannot use this form of the solution. Okay, so that's the first thing. And the second thing is that, okay, why did I consider this u hat of r bar? This basically accounts for a phase shift of the flow, basically. Okay, so it also accounts, it also accounts for the phase shift. The phase shift means that there will be a phase lag between the applied, pressure gradient, which has a amplitude g naught and a frequency of omega, to the actual moment of the flow due to this applied pressure gradient as a result of this applied pressure gradient. Okay, so there will be a phase lag, just the same phase lag that you saw in the Stokes second problem. So this form of solution indeed accounts for the phase shift. And again, in general, the third part is that we seek time periodic solutions. Okay, we seek time periodic solution, meaning that we will ignore the initial transients, rather because we know that the fluid anyway will behave like, will be oscillatory, the fluid movement will be oscillatory in nature. So what we are trying to do is we will ignore the initial transients and then look into solutions where the movement of the fluid is purely oscillatory due to the nature of the applied oscillatory pressure gradient. Okay, that is the idea behind seeking time periodic solution in these cases, in such analysis. Okay, and this is typically the reason why we assume this form of the solution. And I would name this as some equation, let's say 3. Okay, and I hope you are clear on under what circumstances are these forms of solutions essentially valid. Okay, all right. So once this is done, the next task is essentially simple. Next is just the solution procedure. Okay, what you need to do is you need to substitute 3, that is the form of this solution, into the governing equation 2. Okay, so what we'll do is we'll substitute. Okay, I would say substitute 3, that is the form of uz bar of r bar, into 2. Okay, and if you do this substitution, let's see what do we get. Okay, so let's do it. So the first term is this term. Okay, alpha square del uz bar by del p bar. So all right, so what this term would be? So this term would be alpha square del uz bar by del p bar, and I know that my uz bar is equal to dl part of u hat of r bar e power I p bar. Okay, all right, so if I do this substitution, I'll just end up getting alpha square del t of real part of u hat of r bar e power I p bar, and we'll just end up getting what? So we'll just end up getting alpha square. So what do we get? So we'll get, so we just need to evaluate this, and we'll just get what? I alpha squared real part of u hat of r e power I t bar, because this is just a temporal, derivative with time. So we'll just have an I coming out of this differentiation. Okay, the other term is cos t bar. The second term is cos t bar in the equation. So this can be written as real part of e power I t bar, because e power I t bar can be written as cos t bar plus I times sin t bar. So cos t bar is nothing but the real part of e power I t bar. And the third term, that is this term, 1 upon r del r of r times del u z bar by del r. So this, let's see how do we write this term. So this term is 1 upon r bar del r bar of r bar times what? Times del u z bar by del r bar. Okay, all right. And if I now substitute this form here, I will end up getting what? So it will just be, something like this. It will be real part of e power I t bar. Okay, and then it would be 1 by r bar del r bar of r bar times del u hat of r bar by del r bar. Okay, I hope you are with me on this. Just substitute, it's just the substitution that I'm doing here. Okay, but the good thing is, since now this u hat of r bar is just a function of r bar, so I can just now represent this partial derivative with an ordinary derivative, which is just real part of e power I t bar and then 1 upon r bar d r bar of r bar times d u hat of r bar by r bar. Okay, all right. Okay, so once we are done with substituting the individual terms, let's write the governing equations. Okay, so from the first term I'll have this term, which is I alpha square times this, which is basically this. So it is just I alpha squared times real part of, so it is just real part of u hat of r e power I t bar. Okay, and what, and then I have real part of e power I t bar plus real part of e power I t bar 1 by r bar d r bar of r bar times d u hat of r bar by dr bar. Okay, all right. So now what we'll do is, first of all, we'll disregard this real part, but we will keep in mind that once we are done with calculating this u hat bar, we will just calculate its real part. This is the first thing. I hope you are clear with me. So we'll disregard the real part, but once we are done, because u hat of r bar can be imaginary, can be real, or can be both, what we'll do is, we will in general solve for this u hat of r bar and then take its real part as a part of the solution. Okay, that's the first thing that we would do. So we'll just write this. So just by disregarding the real part, we'll just write it at I alpha square u hat of r bar e power I t bar, and I hope you understand the logic why I am disregarding this. This is just e power I t bar plus e power I t bar 1 upon r bar d r bar of r bar times du hat by dr bar. Okay, and then what we'll do is, this e power I t bar will just get cancelled out, and I just end up getting this form as something like this: I alpha square u hat of r bar, and then it just becomes 1 plus 1 upon r bar d r bar of r bar times du hat by dr bar. Okay, and if I just rearrange this equation, I can simply write it down as d2 u hat by dr bar squared plus 1 upon r bar du hat by dr bar minus I alpha squared u hat equals to minus 1. It's just a sheer rearrangement that I'm doing. I just I just used the product rule in this term, and then, brought this term to this side, basically. Okay. All right. So, so basically what we did is, we got an ODE in u hat bar. So just by, using that form of u bar, u of z, of u bar of z as a function of r bar and t bar as a real part of u hat times e power I t bar, we essentially converted that PDE into an ODE of this form. And you need to realize that this ODE, so basically this is equation 4, and this is, so it is an ODE. Okay, so it is an ODE first of all, and it is second order, it is of second order. Okay, more importantly, it is non-homogeneous, because u hat equal to 0 is not a solution of this ODE. So it's non-homogeneous. So it is non-homogeneous, and it we have variable coefficients in this ODE. Means this du hat by dr is multiplied with 1 by r bar. So it's an ODE with a variable coefficients. Okay. So it's an so we have variable coefficients. So this essentially is the characteristic of the ODE that we derive that we saw in this equation 4. Okay. So now the task again is to now solve for this u hat this u hat basically. So because once we know u hat, my my uz bar is just real part of this u hat times e power t bar. That's it. All right. So before going into the solution of this, I will stop here again for some time, and like if you have any doubts, you can ask me. Okay. If no doubts, so now as we all know, the solution form of such kind of ODEs are that my u hat, which is now a function of r, I can basically write it down as a complementary function u hat c. I would call it as u hat c, which is a function of r bar plus a particular integral. I would write it as u p hat, which is of course a function of r bar again. So that's how we derive we solve non-homogeneous ODEs. A complementary function which satisfies so this complement. So I believe you guys know this, that the complementary function satisfies the homogeneous part, while the particular integral takes care of the non-homogeneity in the original differential equation. Okay. So now how to basically evaluate this complementary function and this particular integral is something that we will see now. So first of all, let's have a look at this particular integral. So you know that the particular integral satisfies the entire governing equation. So there are very standard ways of calculating the particular integral. There is something which is known as method of I mean, so I just forgot the name, but there is a standard method of calculating particular integral, which you can look into any. So I just cannot recollect the name. What is there? What actually it is. I'm very sorry for that, but. I think it is called method of undetermined coefficient or something like this. So these are different methods of calculating particular integral. But luckily in this case, we can calculate the particular integral by just having an inspection of this ODE. Okay. So we can calculate this particular integral just by looking at this ODE. This is because of the fact that you can argue that your particular integral. So I'll say that by inspection, your up hat of r is just 1 times I alpha squared. That's it. Why? That is typically because if you substitute this 1 by I alpha square into this governing equation, it satisfies. And it so happened is because since the right hand side is not a function of r bar and it's just a constant, you can say that 1 upon this term is actually the particular integral of this solution form. And this essentially saved us, instead of going into more complex, or instead of going to more general methods for calculating the particular integral. Okay, that was possible, luckily or unluckily, because the right hand side is just a constant, which means you can argue that your particular integral is just 1 upon this I alpha squared. Okay, so that's it, guys. That's the particular integral that we have. Okay, so let's name this. I'll call this as what? Maybe I'll call it as 5. I would call it as 6. Okay. So now we just need to evaluate the complementary functions. And once we are done calculating the complementary function, we basically get the solution of the velocity profile. So the final task is to calculate the complementary function. which is nothing but UC hat of R bar. Okay. So what does the complementary function satisfy? So the complementary function satisfies the homogeneous part of the ODE, which means my UC hat will satisfy D2 UC hat by the R bar squared plus 1 upon R bar D UC hat by D R bar plus, sorry, there minus I times alpha squared UC hat equal to 0. So that's the complementary. So that's the homogeneous part that the complementary equation satisfies. Okay. And maybe I'll name it as equation 7. Okay. All right. So then how do we solve this? So what I will do is we will follow a very standard procedure to basically solve this. Okay. So what we'll do is we'll multiply first the equation 7 by R bar squared. So if we do that, we get R bar squared D2 UC hat by D R bar squared plus R bar D UC hat by D R bar minus I times alpha squared R bar squared UC hat equals to 0. Okay, that's just a simple algebra that we did. Now what we'll do is something that so it's a mathematical trick, but we'll do a very simple mathematical trick to cast this ODE, that is this form of the ODE, into a very known ODE that we will see very shortly. Okay, so what I'll do is I'll do a change of variable here. So I'll do a change of variable. So change of variable. So this change of variable is as follows. Okay. So what I will do is I will consider an R tilde. So I will do a transformation from R bar to R tilde such that my R tilde is R bar times alpha root over I. Meaning that I want to make this as some R tilde square. That's it. That's why I have chosen R tilde as some R bar times alpha root over I. Which means that my D2 UC hat by first let's calculate the first derivative. DUC hat by dr bar would be what? It would just be alpha times root over I DUC hat by dr tilde. That's just the change of, so it's just the change of variable that I am just doing. Okay, it's just the math. So I have just replaced this DUC by dr bar in terms of DUC by dr tilde. That's it. And similarly, I can write down the second derivative at d2 UC hat by dr bar square as alpha square I by d2 UC hat by dr tilde squared. Okay. And then if I just substitute, this form into this equation, okay, I just end up getting an equation for R tilde as something like this. So you can do this substitution. I have already done it, so I'll just write it down. We will just end up getting R tilde squared d2 UC hat by d R tilde squared plus R tilde d UC hat by d R tilde minus R tilde squared times UC hat equals to 0. Okay. All right. So this is the equation that I got once I do the change of variable, basically, or the transformation of variable, or anything that you can say. I'll call this as maybe what, equation 8. Okay. Now there is a so this equation is so famous. This equation is actually so famous that the solution of this equation is well known actually. So for that, what I will do is I'll just make little bit things simple for you. So if I have a variable ux, okay, then if ux satisfies this equation, x squared times uxx, where this uxx is nothing but d2ux. So this, remember, it's just a shorthand form that I'm writing. Uxx is nothing but d2ux by dx squared. That's it. Instead of repeatedly writing, I'm just writing at uxx. So if ux satisfies x squared times uxx plus x times ux minus x, let me write it with the same color, plus, x times ux minus x square minus nu square times u equals to 0. If ux satisfies this, then the solution of this equation, the solution is ux equal to some a times j nu of x, where I'll tell you what this j is and where this j nu is. I'll tell you very shortly. And the other form is, so there are two linearly independent solutions. The other solution is b times y nu of x, where this j nu of x and y nu of x, these are known as Bessel's function. These are known as Bessel function of first and second kind respectively of order nu. Okay, and this equation is essentially known as Bessel's equation. Okay, so that's it. So if you end up getting this equation, you know that the solutions are just Bessel functions, and Bessel functions are some known functions that we have, okay, of order nu basically. So now that if you kind of compare, actually these are not exactly Bessel functions. These are known as modified Bessel functions, because there is essentially a minus sign. Had this been a plus sign, it would have been the Bessel functions. Since there is a minus sign, the solutions are actually the modified Bessel function. Okay, and this equation is also known as modified Bessel equation. But the idea is same. It's just that the form of the functions, they are a little bit different if we have a minus sign here, and that's why they are known as the modified Bessel's equation and subsequently the modified Bessel functions. Okay. So the idea is, when you end up getting a solution of this form, you can rest assured, you can say that the solutions will be either the Bessel function or the modified Bessel function, depending on if I have a minus sign or a plus sign here. Basically, if I have a minus sign, these are modified Bessel functions. Okay, so if you compare this equation and this equation, you can now say that this is essentially, so equation 8 is essentially a Bessel, it's a Bessel's equation of order 0, because nu is basically equal to 0 here. Okay, so because if you just need to compare this and compare this, we have nu equal to 0 in this equation basically. So I'll write it down that equation 8 is a modified Bessel's equation of order 0. And typically in cylindrical geometries, you always end up getting Bessel's equation. Okay, not always, but I would say you frequently end up solving the Bessel's equation in cylindrical geometries. All right. Anyways, so now this means that my solution of equation 8, I can now write it as, so since I know that this is just a modified Bessel's equation, I can say that UC hat of R tilde is just some A1 times J0 of R tilde plus B1 times Y0 of R tilde, where this J0 and Y0 are the modified Bessel's functions of order 0 basically. Okay, so that's it. That's the solution of equation 8, which I will write it as 8a. Okay. Now so the last task is now to just calculate this A1 and B1 from the boundary conditions. So remember, I have a boundary condition there. So if I look at the boundary condition, I said that u bar z, the mod of u bar z is bounded. So this is something that we said. Because of the fact that your velocity profile is finite, not the velocity profile, because of the fact that the magnitude of the velocity is finite, this means that uz is always bounded. Now, this modified Bessel's equation of the second kind, this blows up. So actually what happens is, at R tilde equals to 0, this term essentially blows up to infinity, which means the only way that that my uz could be bounded is the fact that v1 has to be equal to 0. So the idea is, from the boundedness condition, I can interpret that v1 is equal to 0. That's it. That is typically because this form at r tilde equals to 0, this y0 of r tilde goes to infinity, but I want my velocity profile to be bounded. So the only possible scenario is that v1 has to be equals to 0. So this is one constant that we evaluated from the boundedness condition. Okay. All right. So this means that at least now I can write that my complement. So we'll evaluate the other constant very shortly. But before that, I can at least now say that my complementary solution, that is UC of UC hat of r tilde, is some a1 times j0 of r tilde, where you remember r tilde was alpha root I r bar. That's the transformation that we did, if you remember here, right? So which means that if I now again go back to my original variable, my UC hat of r bar is just a1 times j0 of, so now this time it will just become alpha root over I times r bar. Okay. So that's it. That's the complementary solution. So the total solution of u hat, which is u hat of r bar, is the sum of the complementary solution plus the particular integral. It just becomes a1 times j0 alpha root I r bar plus the particular integral. So remember, the particular integral we already evaluated. This is just given by equation 6, which is 1 by I alpha squared. So it is just 1 by I alpha squared. Okay. Now, it is now where we now need to evaluate the second constant, that is a1. So you remember from the no slip condition, I said that u bar z of r bar and t bar, and this I can write it as at r bar equals to 1 and t bar, for all t bar, is basically equal to 0. And I know that my u bar z is what? It is just real part of, u hat of r bar times e power I t bar. Okay. Which means I can straightforward write that, I can just straightforward write from here that u hat at r bar equals to 1 is just 0. Okay. And we'll just apply these boundary conditions here. So if I apply this, what I get? So I get, this means I get a1 times j0 of alpha root I, and r bar is 1, and this becomes plus 1 by I alpha squared, and this is equal to 0, which means I can get the other constant a1 as what? As minus 1 by I alpha square j0 of alpha root I. Okay. That's it. That's my other constants. So this is a1. So once a1 and b1 is known, I know everything, right? Okay. So this means that my complete solution is like this. So my u hat, or how do I write? Okay. So my u hat of r bar is a1, and my a1 is basically this. So it is minus 1 by I alpha squared j0 of alpha root over I times this term j0 alpha root over I bar times j0 of alpha root over I r bar plus the particular integral, which is 1 by I alpha squared plus 1 by I alpha squared. Okay. Which I can, maybe write it as minus j0 of alpha root over I r bar times I alpha squared j0 of alpha root over I plus 1 by I alpha squared. Okay. That is u hat of r bar. So The total solution now is, so that is u hat, but we need uz of r bar t bar. So your uz, okay, of uz bar of r bar t bar is just, if you remember, it is just real part of u hat of r bar times e power I t bar. So this just becomes, so the total solution uz bar of r bar t bar is just real part of this term u hat bar of real part of u hat, which is this. So it is minus j0 times alpha root I times r bar, okay, by I alpha square j0 of alpha root I, okay, plus what, plus 1 by I alpha squared, and this is multiplied with e power I t bar, okay, that's it. So what you need to do is you just need to evaluate this and then take the real part to get the, complete velocity profile. So that's it, guys. So that's the non-dimensional, that's the non-dimensional velocity profile. Okay. Now you can appreciate that. See, the non-dimensional velocity, and this is where lies the beauty of non-dimensionalization. So you can see here that just by fixing the parameter alpha, which is the frequency dependent Reynolds number, I uniquely get my velocity profile uz bar. It is not a function of which fluid to choose, rather it's a function of what the frequency dependent Reynolds number is. Okay, so it makes the analysis universal, and from here also you can simply get the dimensional form by just substituting just by writing the non-dimensional variable as the dimensional variable. For instance, if I just write my r bar, so I can simply write my r bar as r by r, okay, and I can simply write my t bar as omega t. So if I just substitute this r bar and t bar into this form, I simply end up getting the dimensional solution, the dimensional solution of uz as a function of r and t, basically the dimensional variable, to be precise. Okay, so this means that a non-dimensional approach is more general. Basically, you calculate the non-dimensional profile, just use the characteristic variable to get the dimensional profile. And what you can now do is, as an exercise, do this problem dimensionally. This will be much more easier because you don't have to deal with the scales, and you can then compare from this result and the dimension result, that you will indeed get the same, you will exactly get the same result. Okay, and this is something that you can do it at your end. So that's it, guys. So by doing this exercise, I hope it gave you a flavor of certain things, the understanding of scaling analysis, and how to basically look into one unidirectional time periodic solutions in by solving the Navier-Stokes equation. So I'll end the discussion here. If you have any questions to ask, you can ask in the discussion forum of the group, or in the next class. Okay, so I'll end the discussions here. Thank you very much for attending. We'll meet on the next Saturday at the same time using the same link. Thank you very much, guys.